The research topic covered by Alessandro Magnani is related to the design of integrated phase locked loop for medical applications and video diffusion. The research activity was carried out in the frame of a co-supervised PhD contract with the University Paul Sabatier in Toulouse. Alessandro Magnani is developing two PLL. One is designed in 130 nanometer CMOS technology and is focused to broadcasting satellite communication, DVB-S satellite. And the second PLL is focused on the realization of the modulator for millimeter wave applications, specific for broadband communications for video and medical applications. This is a brief introduction of the work. The state of the art today is PLL. I'm speaking about DVB-S, of course. The state of the art today is a local oscillator realized with a DRO, I mean dielectric resonant oscillator, typical realized with discrete components. So it's very expensive in terms of size, and even also in terms of cost. And the receiver is usually realized with compound semiconductor amplifiers, typically using high electromobility transistors. The idea behind this activity is to replace the system with silicon-based technology in order to reduce the size of the electronics and even the cost. The proposed solution is described in this figure, where the PLL is the main device designed by Alessandro Magnani. Here on the right bottom of this slide, you can see the building block of the designed PLL. The structure is very classical one. We have a phase and frequency detector, charge pump, loop filter, the voltage controller oscillator, and the frequency divider on the feedback loop. One of the main important constraints given by the DVB-S standard is the phase noise of the local oscillator. So we start from this point. And here we have the simulations of the phase noise with the contribution of each building block. The PFT, I mean the phase and frequency detector plus the charge pump, the prescaler, the VCO, the reference, and it is compared with the standard of the digital video broadcasting satellite. So we can see that in these 2 decades, I mean from 10 kilohertz to 1 megahertz, the phase noise is higher than the standard. This is the realized chip. You see that the size is about 1 millimeter square. And we have integrated on this chip all the PLL together with the buffer to drive the output instruments. And here on the right side, upper side, you have this building block of the characterization setup. And the PLL is currently working at 15 gigahertz. It is consuming about 100 milliamp from 1 volt of polarizations. And the locking range span between about 14 and 15 gigahertz. This is a comparison between the simulated and measured phase noise. In fact, we obtained a very good agreement because to measure the phase noise at 15 gigahertz on a naked die is a very difficult task. So in fact, the comparison is very good. And therefore, this means that the PLL is currently working. In order to improve the phase noise, the first step investigated was to increase the current of the charge pump. In the actually realized prototype, the charge pump current is 25 microamp. And in simulations, we raise this charge pump to 300 microamp. And we can see that we have a interesting improve of the phase noise, especially in this frequency range where we were away from the, we are far from the standard. In fact, we see that if we compare the phase noise simulated with a charge pump of 300 microamp, we are not, in fact, not really so far away from the DVBS standard. So in fact, this is demonstrating that, in fact, today, the silicon technology is very promising to realize a receiver for a DVBS standard. The only commercial product realized, partially realized in silicon was fabricated by Infineon, and the foundry was using silicon germanium technology, which is more expensive than the CMOS we are using here. Here the technology used was a bulk pure CMOS. No bipolar transistors were used. This is the second topic of the research activity carried out by Alessandro Magnani. Again, the attention was focused on the frequency synthesis, but in this case, the targeted frequencies are very much higher. We are moving from the 15 gigahertz of the previous applications to the 60 gigahertz millimeter wave frequency of these applications. And here we have a building block of the receiver. We have the 20 gigahertz reference, the relay, the down conversion mixer, and the intermediate frequency bandpass amplifier. In particular, it is very important to be able to correctly drive the mixer, the down conversion mixer, and operating at the high frequencies. In this kind of approach, it was chosen to use a pulse generators. So in this case, the pulse generators is driven by the local oscillator working at 20 gigahertz, and the pulse generator generates pulses at the double frequencies at the output. So this is the schematic of the pulse generator. Of course, in this case, we are using bipolar transistors because working at the high frequencies, in fact, CMOS is quite too much difficult, quite hard. And this is the schematic, as I said before. It is realized with two amplifying stages, one in class C, which is in fact generate the pulse, and the second stage is a class A stage, which is responsible for an inversion of the pulse. This is a comparison of the obtained pulse comparing two solutions. One solution was using inductor, and the other solution was inductorless. Because the interest of these investigations, because an inductor in terms of silicon area is very expensive. It's very large. So in this case, it is always very interesting to investigate if it is possible to realize the solution inductorless. But we see that in this case, it's not possible avoid the use of inductor, because without inductor, it is the blue curve, the pulses are too low. With about 250 millivolt, we are unable to correctly drive the down conversion mixer. So it was necessary to use inductors. The chip becomes more expensive, but the performances are better. This is the layout of the realized integrated circuits was realized in a 130 nanometer technology, but it was a BiCMOS technology, silicon germanium by IBM. The spirals on the chip to reduce the rise and fall time and to enhance the amplitude of the spikes of the pulse. And because of the so high frequencies, it was also required to extract the layout parasitic using electromagnetic simulations. So in fact, it was a very, very huge work. And this is the layout of the complete prototype. The dimensions are about 2 millimeter by 1 millimeter. So in fact, about 2 millimeters square. And the prototype is now in characterization. Alessandro Magnani is not here today because he's characterizing the prototype now. The characterization started this week and should be concluded by the next week, because we have an advanced meeting for this research scheduled for the 21st of January. So in fact, the times are very, very short. This is why Alessandro is not here today. As future works, of course, Alessandro will start to write a paper summarizing the work carried out on the PLL for DVBS applications. And of course, for the millimeter wave PLL, the first step is the characterization of the prototype and possible redesign after the progress meeting of the next 2 weeks. Okay, that's all. Thanks you very much for your attention. If you have any questions.
It's okay. Thanks, Mattia. And the next candidate is Marius Octavian Olaru. Then we have other two presentations, and this will conclude the program of this afternoon.
Non stare sul primo slide.